Hi, let's go a little more in depth into ionic bonding, some specifics. So with ionic solids, you know that it's a metal and a non-metal. For example, here I have a sodium and a chlorine. Now those come together in an intramolecular force, an intramolecular bond. Those atoms held together in a compound, Remember, on ionic compounds, we never use the word compound. We will use, if we're being very, very technical, the word formula unit. So sodium chloride, I would say sodium chloride formula unit. Do not use the word molecule. These are not molecules or formula units. And if you're not sure, just use the word compound. Compound is a safe umbrella for any two atoms that are bonded together. All right, so metal, non-metal, that force, that intramolecular force that holds the atoms together is called an electrostatic force. And this is simply the positive of the cation is attracted to the negative of the anion. They're like baby magnets, but don't be fooled. That positive and negative is crazy, crazy strong. It's like magnets on steroids. Just to make sodium chloride, so table salt that you and I eat, just to make that change phase from a solid to a liquid, to melt. That's all. Think about ice melting. Ice melts at 0 degrees C. Just to make sodium chloride melt, we have to heat it to over 900 degrees. Wow. So this electrostatic force, super duper strong. So our ionic compounds have really high melting points and boiling points because of this electrostatic force. They're brittle. So if we have a mineral, an ionic compound makes a mineral, and we hit it with a hammer, it's going to break on straight lines. That's what brittle means. Let's write that down. This is going to break on straight lines. Straight lines. And here's the reason why. It is the Coulombic attraction. All of ionic compounds, you're going to explain it with Coulomb's law. So notice I began writing the crystal lattice. So the crystal lattice is positive, negative. There's your compound, but then you have another compound next to it, positive, negative. It's because this sodium that's positive will also be slightly attracted to that negative of the chlorine in the first compound. So beautiful, all by themselves, because it's energetically favorable. Ionic solids will line up positive, negative, positive, negative, positive, negative in a 3D structure. So imagine if I had another layer over this, you'd have a chlorine and then a sodium, and here a chlorine, then a sodium. So at any one point, you could look at one ion in a compound and it's surrounded by opposite charges. It's going to have 6 opposite charges around it. Wow. Now the reason why this is brittle, if we hit this, if it shifts down just one, look what would happen. We would have a sodium and sodium next to each other, the chlorine and chlorine next to each other. Well, that actually repels. So it shifts down one more so that you still can maintain the positive, negative charge, positive, negative, positive, negative. So notice the description I gave. Ionic compounds are brittle because the repulsion of like charges, up here I had the sodium, and there was the chlorine. Repulsion of like charges when the 3D structure shifts down. So it'll shift to try and maintain as much of the positive, negative, positive, negative, positive, negative interaction. That's why they're brittle. Pretty cool. Now these are soluble. Take that with a grain of salt. And I did not mean that for it to be a pun. It just barely hit me. Most are soluble. Now when you get into KSP, you're going to learn about some ionic compounds that they will not dissolve, or they barely dissolve. For all intent and purpose, you can say that ionic solids are going to dissolve in water. Are there exceptions? Yes, it's our solubility rules, but that's for a different discussion. They will conduct electricity when they're dissolved in water. So notice I put this as aqueous, meaning we've dissolved salt, sodium chloride, in water, and as a liquid. So if I were to heat up sodium chloride to over 900 degrees, it becomes a liquid. It could also conduct right then. Now, if I have just a pile of salt in a petri dish, solid, salt that you and I could eat and put it on our food, put it on our French fries, if I put a conductivity probe in that, big fat nothing, it won't conduct. The reason why ionic compounds will conduct dissolved in water or as a liquid is because the ions are free to move. Now remember, electricity, current, that is electrons moving. So because electrons, these ions can move, it means that the current can conduct. Those electrons can move. Not ductile or malleable, so you can't stretch and pull ionic compounds. You can't bend them, and they're very hard. They're very, very hard. One thought just came to me. I use that term salt. I'm going to add it right up here by formula unit. We do have a nickname for ionic compounds. We will call them salts. Now, in the vernacular, in layman's terms, when we say salt, we mean table salt, sodium chloride, that we eat. But in chemistry, when a chemist says a salt, they simply mean an ionic compound, a compound with a metal and a non-metal in it. Okay, so let's focus just a little bit on ionic crystal lattice. So I had drawn a crystal lattice right here for you, and you're expected to know how to draw this, and it's really easy. It's just going to be cation, anion, positive, negative, always is how you draw it. So I see that anion, I'm going to put the cation. And all of these are, I've got written right here, 1, 2, 3, 4, 5, 6, 7 compounds. But they're going to align themselves positive, negative, negative. Now, a cool thing. From this, we have what's called the lattice energy. Lattice energy. And here's the really neat thing about lattice energy. We could take the individual energies for each of those compounds and add them together, okay? And then we test the energy of that entire crystal. The energy, that's going to be the lattice energy for the whole crystal. The lattice energy is greater than the sum of the individual compound energies, which tells us there's a little bit of interaction, potential energy, between the compounds themselves. So there's actually greater energy when they're together than when they're separate. Cool, very, very cool. That could be a metaphor for life. I like that, we're stronger together. Okay, so the ionic crystal lattice, notice that maximizes attractive forces and minimizes the repulsive forces. So it's focusing on those positive, negative, attractive, rather than a negative, negative, or positive, positive repulsion. And this is all based on Coulomb's law. So a little reminder, here's Coulomb's law. Potential energy, that's your VE, is charge 1 times charge 2. So in this case, it's going to be the positive times the negative. It's going to be the cation and the anion is what we're looking at for our charges, divided by d squared. And d is going to be the distance between our atoms, okay? It's going to be the distance. And so you're thinking the electron is going to be attracted to the proton of the opposite nucleus. Let's see here. Another way to think about it, sodium loses an electron, chlorine accepts that electron. Now it's after they become ions that they attract. Because this has one more proton and that has one more electron, they're going to come together and attract. And so it's that positive, negative, that's going to be your Coulomb's law, the Q1 and the Q2. Now distance, so the distance between these atoms. The smaller the atom, the greater the potential. And you can see it right here. The smaller the denominator, the larger the quotient. So the closer those atoms can be together, the greater the energy. That's going to be really important. So a really common question that you'll be asked is you'll be given ionic compounds and you have to determine strength. And that could come in many forms. It could be highest melting point, highest boiling point. It could be which one's harder. That would all fall under this idea of strength. So you go to two things and they both fit inside of Coulomb's law. First thing you always look at is the charge. Okay, so I said number 1 charge, that's the numerator right here. Now if the charges are the same between your two ionic compounds, then you go to size. And that is the smaller one, okay? The smaller atoms, there's going to be closer together, are going to have a larger potential, so they would be stronger. Let's do a couple of examples with this. Let's take our sodium chloride, and I'm going to compare it to sodium chloride And let's compare this to a potassium bromide, okay? And I want to know which one has the higher melting point. So I look at charges. Number one, I always look at charges. So sodium's a +1, chlorine's a -1, potassium's a +1, and bromine's a -1. They're the same. So then I have to go to number 2, and I'm looking at size. So you will recall from the periodic table that atomic radius increases as you go down the periodic table. That's also true for ions. As you go down the periodic table, you add a whole nother energy level, so it makes the atom bigger. So let's look. Here's sodium, it's in period 3. Chlorine is in period 3. And then we've got potassium period 4, bromine period 4. So which one's smaller? It's the sodium chloride. So this would have the highest melting point because it's going to have the greatest energy, the greatest Coulombic attraction is going to take more energy to cause it to change phase from a solid to a liquid. Okay, now let's do another one. Let's take our sodium chloride again, and this time I'm going to compare it to, let's do a potassium sulfide, okay, potassium sulfide. So first thing we always go to is charges. Really, really interesting. With the charges, it's pretty easy to see that there's a direct proportionality between charge and potential energy. If you double the charge, you double the potential energy. Wow. So charges, we've got a +1 and a -1 for the chlorine. Potassium's a +1, and our sulfur is a -2. So instead of going 1 × 1, I have 1 × 2. We just doubled the energy. So I would say on this, don't even have to look at size. Charge trumps. So looking at this, the potassium sulfide would have the highest melting point, or highest boiling point, or be the hardest. It would be the strongest because it has a greater charge. So that's always how you're going to look at ionic compounds to decipher, predict strength. Okay, very good, ionic solids. Keep going there, that you can look at intermolecular forces. That's going to be for molecules, and then you can also look at the metallic solids, and that will bring all the bonding that you need together for a first-year chemistry class. Have a good day. Thanks.